we are going to have two examples of Maclaurin series and Taylor series taken out to their full conclusion. Back in the section called Taylor and Maclaurin series part 1, we learned how to take Maclaurin and Taylor polynomials and extend them to an infinite number of terms, and ta-da, we had Maclaurin and Taylor series. In that section, we had a video example where the Maclaurin series for the function 1 over x minus 1 cubed was developed, and it turned out to be this thing. In this second part, Taylor and Maclaurin series part 2, we've been going back and taking these Taylor series and Maclaurin series and learning where we expect convergence between the infinite series we've developed and the given function. For different functions and different series, we have intervals of convergence that are the entire real line, that are from -1 to 1, that are from 0 to 5, right? There's all sorts of things that can happen. And very often the key to that interval of convergence is the ratio test. So this particular series has already been developed. You can go back and review the video in that part 1 section if you would like. Here we're going to follow up by determining the interval of convergence with the ratio test. Going to name the coefficient part of that series as a sub n in preparation for the ratio test. The other part to get ready for the ratio test is to build the term that would be a sub n plus 1. And since we're going to put these in absolute values, here I'll build this ahead, we're going to build the ratio a sub n plus 1 over a sub n within absolute values. So that means we don't have to deal with this -1. So the version of a sub n where n has been replaced by n plus 1, well, it's still all going to be divided by 2. What used to be n plus 2 is now going to be n plus 1 plus 2, which is n plus 3. And what used to be n plus 1 is now going to be n plus 1 plus 1, which is n plus 2. And we will have the x to the n plus 1 tacked onto the end of it. I guess I drew my brackets a little bit too small. So we're going to make our ratio the magnitude of a sub n plus 1 over a sub n. Can we agree that when we do a sub n plus 1 over a sub n, that divided by 2 is going to cancel in both, and we don't have to write it down and then cancel it? We'll just plan ahead for it not being there. So what's left behind from a sub n plus 1 is going to be the n plus 3 times n plus 2 times x to the n plus 1 divided by the a sub n, again recognizing the over 2 part's already canceled out. That'll be over n plus 2, n plus 1 times x to the n, and put absolute value bars here. We do need to keep those around because we don't know what x is going to be yet. X could be positive, it could be negative, and so we do need to keep the absolute value bars. There we get a little bit of cancellation all together. Now the n plus 3 divided by n plus 1, which is surviving here, we don't need absolute value bars around that because n is always positive or 0. But that quotient will always be positive. And then from the x to the n plus 1 divided by x to the n, well, that's just going to simplify to the absolute value of x to the first. And remember, the key to the ratio test is that the limit of that ratio that we just built, which is going to be the limit as n goes to infinity of n plus 3 over n plus 1 times the absolute value of x. That has to be less than 1 for convergence. Now the limit as n goes to infinity of all of this will be the limit as n goes to infinity of this quotient, which is 1 times x. So we need 1 times the absolute value of x to be less than 1 for convergence, and that's just the absolute value of x is less than 1, and so that corresponds to the interval from -1 to 1. Now the footnote about the ratio test in this context, when we're dealing with power series, that is very often forgotten, so don't forget, is that we need to go back and check the endpoints of this interval we've just developed one at a time to see if either of the endpoints leads to convergence. So, at the endpoint x equals -1, basically we have to hit the reset button and go all the way back to the top and say, all right, we're going to look at that point in particular. The summation is going to be, well, when x is -1, this will be -1 to the n times another -1, so that'll be -1 to the n plus 1 times n plus 2 times n plus 1 over 2. And one of the first things we learned about infinite series is that if the size of the numbers you're adding up isn't going to 0, there is no way you're going to get convergence. Even in an alternating series, you still need the size of the things you're adding up to be going to 0. Now, these things are getting bigger and bigger. N is going to infinity, and you've got n plus 2 times n plus 1. So that's not going to converge. And hopefully you'll agree that at the other end, if we go take any x equals 1 and plug it in back up here and see what the series is, it'll look very much similar. We're still not going to get convergence. And so the interval of convergence here, can we still see this? Yes, we can. Is every x value between -1 and 1. That's the place where if we were to look at this function and also develop this series, the two functions represented are going to converge to each other. Now I have a window over here. Look at the top part of, whoops, I did these backwards. Look at the bottom part of this screen where I've plotted 1 over x minus 1 cubed. That is the red curve in this picture. And I've also plotted the first 21 terms of this summation into a hideous polynomial, and I've plotted them both on the same axes. The blue curve is the Maclaurin, now it's a Maclaurin polynomial because we only have 20 terms, and you can see between -1 and, well, almost a -1, but it's doing a pretty good job, although it's losing it as we get closer to -1. I wonder what happens if we make this. This is the great thing about using tech. Whoops. You're already seeing the giveaway up there at the top to the next question, so ignore that for a second. I'm going to plot 200 terms. Okay, I'm going to come over here and re-execute the plot command. And look at that. That's much better. You can see here the convergence between the blue curve, which is the Maclaurin polynomial. Now it's a big polynomial. And the red curve, which is the actual function, almost exactly to -1 before the polynomial says I'm out of here and does something totally different. So that's your interval of convergence in action.